I was very ambitious at the beginning when I said that I'll talk about modeling in electron microscopy and thought to talk about several topics in that, but I'll concentrate only in the simulation of the electron beam passing through the specimen. So I think that this was used already by John, so everything starts from this microscope, but now the microscope looks like that, much larger, much bigger, and much more expensive. So the thing is how this works. So how we achieve actually much higher resolution than the visual microscope, and of course everything comes with a price. So there are two basic ways of working on the transmission electron microscope. It is the conventional one, which has the parallel beams going through the specimen, and then we have the result in the end in the kind of the matrix of pixels, or we can just observe one single position. That means recording one pixel information, but scanning through the whole material. So because the second one is more computationally interesting, because it has much more things to be done there, I'll consider this model, but just saying that conventional transmission electron microscopy also can be simulated in the same way with slightly different approach. So let's consider what is the scanning transmission electron microscope. We have usually the specimen, we concentrate the beam in a specific position there, and then on this position we measure the scattered electrons which actually interact with the specimen, and then eventually, because the kernels are charged positively and we have a negatively charged particles, they eventually are diverted on their way down. So when this happens, depending on the angle, we have different detectors. One is the bright field detector, and the other is the dark field detector. That is kind of the basic operation. In addition, which I probably will talk in my other talk, it is about some other information. This is an EDX detector. I will not talking about the modeling of how the EDX detector happens, because it is based on the fact that when the electron beam hits the atoms, eventually it takes away some of the electrons in the shell, and because there cannot be a lower orbital empty space, so the high orbital electron is going down and filling it, and then emits an X-ray, so which is kind of measuring, but as I said, it is very hard to model exactly that happens. Usually that is some probabilistic modeling at that point, and this is what people say, okay, based on experiments, we know that when we actually hit the material with the electron beam, certain number of electrons gets displaced, and then we have this X-ray detection. As I said, I will not talk about this, simply to say that this model is only for this process. And then, of course, there is also energy loss spectrometer, which is measuring actually what is happening below the bright field. So what are the challenges? First, the light microscopes, it's very easy. They are formed from they have positive and negative lenses, and because of that they can concentrate very well the beam, and there is no aberration. However, the electron microscope, they use electromagnetic lenses, and if they're radially symmetric, that means they could be only positive lenses. So it is impossible to have, and I think that yesterday it was mentioned already, that it's impossible to have the radially symmetric concave lenses, electromagnetic lenses. So you have to use multiple system to actually be able to mimic what the lenses do, and then to have eventually the aberration correction. The aberration correction is very important because that makes anything well built for especially if we want to make the simulations. And often we will assume that everything is very well aligned. There are two things. One is the spherical aberration, which means that if the beam is going a little bit out of the center, then it would divert. It will go a little bit away from the center. It will not be aligned the same way as the others. That is the spherical aberration. And then you have the chromatic aberration when you have some small differences between the speed of the electrons. So the one which are with higher speed eventually will end up in somewhere else. They will focus on a different point. This one usually in the models, unless we want to investigate, especially what happens in this case, we don't do some special efforts for that. So the basic thing is the modeling the interaction of the particles which are in the specimen with the electron beam. Considering all the particles, that means all the billion electrons which are going through the material, and all the particles in the atoms, which would be very good project, it's of course impossible because that becomes too complicated. So the way we're doing that, we're considering a single electron going through the material and how it interacts not with all the individual particles, but with the electrostatic field which is on that place. So what we're doing, we're considering the interactions of a single electron with the electrostatic field, and then consider what is happening. So in order to do that, so one thing we're using is that the velocities of the electrons of the beam are very similar, and that means the interaction between them are not essential. And we will also consider the electron beam eventually will end up with a linear equation, and this linear equation we combine many electrons and consider the wave of the whole electron beam instead of considering just a single electron. So let me, another thing which we assume is because this electrostatic field we consider in the sample is actually composed of several atoms which have temperature vibrations. So because if we are not in the 0 Kelvin, then these vibrations will be there. That means they will not be exactly at the center, the expected center of the atom. They will deviate from that in unknown matter. So to do that, first, so it is possible to get a stochastic model for that. I actually tried. It's a little bit more complicated than you want to be. So that's why it is possibly the the basic way this is considered is the following. We have the average positions where the atoms are expected. Say, if you think about the crystalline structure, you have your perfect crystalline structure. You say, okay, here are my atoms. And then you say, okay, we have some probability distribution, which tells us how eventually these atoms can move. You consider them absolutely independent of one another. And then you assign just small distortions of the positions. So you compose all these atoms. You consider the field that they are creating, and then you run your simulations for this field. When this is done, you repeat that 100 times, and then average the result. The thing about the average is the following. While we're considering the first portion, when we're considering the electron wave going through the material, this is a linear process. At least we simplify it to a linear. And this linear process, we can easily do some linear combinations and do this and that. However, when we want to see what is happening after the electrons exit the sample, when they are going to the detectors themselves, they detect in a nonlinear way, which means that the linearity is lost, and then we have to consider this process to consider the results and then average. We cannot average on the previous stage because the previous stage makes it linear, but then because of the nonlinearity of the process, we'll have not the same result. So that means, okay, let's make some count before going through that. So let's consider so far what we're saying. We're saying that we're scanning the electron beam is scanning. Usually, say, if you're modest, you have about 1 million pixels. If you're not, you have 25 million pixels you want to scan. So you have this many positions. Then you have to repeat, you have to solve some differential equations. We're coming to that. And then this 25 million times. Then another 100 more, just because to get away from the frozen phonon simulation. And you end up with huge number of simulations you have to perform, and keep in mind that the equations you have to solve is not very simple to solve, so that will require some time. So just to simulate what is happening with one signal probe, so to see what is going there, you'll need tremendous amount of computations. So we have to go something to simplify what is there. So what is we're now talking about the modeling of this interaction of the electron beam with the sample. So we consider the electron wave function, which is three variables, x, y, and z. So the z is the thickness of the sample, so x, y. We consider flat two-dimensional electron waves. So we have the initial wave, which is at 0, that is on the entrance of the material, and then we consider different waves for different positions, because, as I said, we have several positions in the scanning. And for this, we have these initial functions. And then we consider what is happening with the electron waves of these electrons. And immediately we mention that say about the typical energy is 200 kilovolts, which is a little bit more than half of the speed of light. And that means there are a lot of relativistic effects. And the proper equation to model these interactions is the Dirac equation. And in order to solve it, then this psi function, which is considered as a vector of 4 complex numbers, which describe different things, and actually, oops, sorry, which you can see from this excerpt from the paper, actually, which argues that probably it's better to use the Schrodinger equation. So that is the Dirac equation, and this psi here is actually 4-dimensional complex number for each value, and then we have these matrices. This is A, is composed of 3 matrices actually. The beta is this matrix, and then you consider the interactions. It is not an easy equation to solve. So why people use it? They eventually solve for particular setups and then compare the results with the Schrodinger equations, which is much more simple, and see what are the errors eventually. But this is done only to kind of justify the use of the Schrodinger equations, because if we start calculating that, it would be too much. So what is the Schrodinger equation for the fast electrons? What I wanted to say, it was written there, but this equation actually is changed a little bit, so it's made relativistic. So that means it has the relativistic speeds and the relativistic masses, so that is corrected in the coefficients of the equation. It's considered, of course, in general, but let's see what, and now psi is only one complex variable, so that is much more simple. R is x, y, z, simply not to write them all the time. We have a Laplacian because we consider interaction with the 2-dimensional waves. We consider the 2-dimensional Laplacian, and then VR is actually the electrostatic potential of the specimen. So which is complicated function. So in the experiment we ran, we had, say, 55,000 atoms, which you have to describe this electrostatic potential through all these atoms, and of course that all should be calculated. So the goal of all this operation is to get the solution of psi for all the values, and then to get what is happening when this exits the sample, the specimen. So when it exits, we assume that there are free electrons, no significant electrostatic interactions, and then these electrons, actually we have to calculate the exit from that. So as I said, because this, if you consider this equation, it is linear if we consider it as an operator from which we receive from the initial wave to receive the exit wave. And if we have linear combination of these functions, then the result would be linear combinations of that functions in solving the equations. So this linearity actually helps a lot of simplifying the things. And then in addition, as I said, it is relatively close to the solution of the Dirac equation, the results, the essential results. So that's why we can do it. The next point is, and I want to say that for the conventional electron microscopy, we can consider the same equation. Simply, we change completely what is the initial wave. The initial wave, the electron wave, would be then spread around. And then, of course, we'll treat the exit wave in a completely different way to receive the results. So that is what is happening. And there are a few points what we have to do. First, we have to see what is our initial wave. Because, of course, we have to model that based on how the electron microscope looks like. Then we have to calculate what is the electrostatic potential of the specimen. And then we have to solve the Schrodinger equation with the initial condition here, this electrostatic potential, and receive the exit wave as evaluating the solution at Z. So for those of you who love deep learning, I'll give you a problem here. Make a deep neural network that actually obtains directly the mapping from the initial wave to exit wave. That's something which sounds interesting. I don't know whether this is really possible, but probably that is one thing, at least for some simple problems, can be tried and to see how successful that would be, because that will give you faster computations of that. Actually, I would go a little bit more, saying, okay, instead of considering that, why don't we consider just going from the initial wave exactly to the result? So that is something which can be explored. I'm a little bit skeptical that with the current way the deep learning is, the current stage of the deep learning development, it would be possible now, but I wouldn't say that in 10 years. So in 10 years, probably there could be ways to actually circumvent all these calculations somehow and see what is going on. And then the last step, which I say, okay, how from the exit wave we receive the results? If we have the bright field, we simply integrate the square of the Fourier transform of the exit wave on a circle, which actually represents the bright field. And then if we have annular dark field or high angle annular dark field, that depends here of the radii R1 and R2, whatever we'll say, that we take that. I believe if we have a 4D microscopy, there are also formulas which actually describe each pixel, how to calculate that. So that is an important calculation is this one here, and we want to do it how it. So I'm using the slides of.
I have a question about this deep learning method.
Yeah.
So really, do you mean a mapping from the initial guess at the electrostatic potential?
No, I'm thinking of the following. We have a lot of parameters, and these parameters are describing what are the atoms, what is the position of the atoms. Then, based on that, we can train a neural network which would receive the results.
But you don't really gain anything if you train a neural network on one particular specimen, right? Because then you already
you have to train it for several others. But I'll talk a little bit about this a little bit later, when I say for the further development.
There's a set of papers over the last few years by Christoph Koch solving the inverse problem using an artificial neural network, trying to go from the exit wave to the positions of all the atoms, rather than the other way around.
So how successful?
It sort of works with perfect noiseless simulated data.
Okay. No, that's at least something interesting. Yeah.
I want to make a comment. But this is kind of from mathematics point of view. This is not a unique problem. Let's say you have atom differently. You try to get from 2D image, you get 3D instruction from 2D. The information has to be conserved, which means you cannot get something from nothing, right? So you get a little things. So the number of the equations have to be more than unknown variables. So it depends on how really. So.
But I think the approach is similar to the Van Dyke and Chen phasing.
Yeah, but that's a special case. This is not very general. Just same as enclosed symmetry. That's not a very general.
But
Yeah.
using
You have to put a lot of conditions
You have to
in order to
constraints,
invert.
yes,
Yeah. In order to invert it successfully. I'm not sure how that should be done. But yeah. So I just want to say that Christian contributed to some of the schemes and for further on, but okay, and I'm going to criticize him. Sorry about that. So about the scheme, it is not to scale, of course. So but this is just to help your imagination. So that is the electron beam. Keep in mind that this should be very, very narrow, and that is kind of the objective lens. Usually, it's relatively narrow comparing to these lines here, but it's a perfect scheme to say. So we have three components. One is the objective lens, which is focusing the electron beam on the sample. The second one is the specimen, the transmission and scattering of the electrons here through the sample. And the third one is the detectors, a recording of the electrons. So there are two detectors. This is kind of the annular field, and this is just a circle. So let's consider that one by one. So the objective lens is the probe wave function is usually calculated. This is the inverse Fourier transform of this exponential function evaluated at x minus p, which that means it's eventually shifted by the position of the wave. We consider this to be approximately the same, and I think that more or less that is true, even if it is moved by the electron microscope, the differences are minimal for that. Okay, here in the objective lens, we have, this is the function, this is the aberration function calculated to the fourth term. I think that it could be better, but eventually that is what is used. And then you have the aperture. This is probably the most important thing which we have, and that actually governs the numerical solution of the problem. This is practically saying that if you have that the waves numbers are bigger than alpha, then you have to cut this out, so you don't have high frequencies. This is a band-limited signal, basically. And here we have the proposition, of course. So then the second one is what is happening in the specimen, and in the transmission of the electrons, we have the PDE. This is the Schrodinger equation. We have the initial condition, and here just R means the XYZ coordinates. So we have the lambda is the electron wavelength here. I, of course, is the imaginary unit. Sigma is the beam sample interaction constant here, and this is the electrostatic potential of the specimen. So the electrostatic potential, just for a single atom, is calculated through some given constants, which are very well known. I think that you can find them, in particular in the Kirkland's book, which I'll cite a little bit later when talking about the multi-slice algorithm. And then after you have this, you can calculate one potential, then combine everything, and have the electrostatic potential whole specimen. And then when you, so you just use that function, and this is the equation you have to solve. So the detectors, then they depend on the squared amplitude of the Fourier, in the Fourier space of the electron wave, and you calculate, depending on what is that, as an annular fields. As I said, you can also consider some different forms, say for the stem, you can do that also. This is the summary of what I talked. So that is what we're solving. And now the basic thing is how to solve this equation. So there are methods, especially this problem was considered in the 60s. At that point, the only method to solve it was the Euler method. I mean, the only way people were considering this type of equations to be solved is just progression in z direction, which was considered the time variable, and then step by step calculating the approximations. Eventually, what I was talking about here, this is the very important thing, that okay, it's a little bit before. So this aperture function, this is very important because limiting the wave number actually stabilizes the solution of the equation. So, but nowadays there are a lot of methods to solve this equation, and actually that would be interesting to solve it, which at some point I may try to develop the methodology to solve it. The thing is whether it is worth it or not computationally, because that could be very computationally intensive. And then the last thing, the thermal vibrations, the frozen phonon approximation, we have to repeat these computations all the time. So that means solving the equation has to be repeated not only for every position, but also at least 100 times for one. And I want to give you just an example. This is zeolite, so that is some old paper in which we did some special processing of the micrographs to receive some better image, because it is very soft material. They got actually, I think we did 32 micrographs, but only the first 9 were good. The others were already damaged by the beam. But we used the first 9 to get this structure, and this is the single frozen phonon simulation. It is not averaging 100 times. That's why it is so sharp. This is the centers of the atoms. So how that looks like, and that seems relatively the same. Why I want to mention something else, because here there is something from the modeling we are using. This is the position distortion. So during the acquisition of during the scanning process, actually the positions which we assume the beam is there are not exactly the same. So that means if we want to make a simulation, we of course assume that the positions are the same. We cannot make random distortions because they will differ from what happens in practice. So that means we have to do some inverse modeling, in a sense, to compensate for this position distortions through this non-rigid alignment, which we did at that time. So now I want to talk about the basic method of solving the differential equations. So that is the multi-slice method. As I said, this is the the Euler method, we just propagating the wave, making the approximation for each step, and then eventually consider that. As I said, the stabilizing effect on this process has the band limitation, because whenever we make the step, we consider the Fourier transform, whether this is on the same, and take out all the high frequencies. The useful feature about this multi-slice algorithm, which is, I think it's not enough advertised, it is that the fact that we want to have a very thin slices in z direction will assure that there are not two atoms in the same slice which have close x and y directions, which means the calculation of the v on this thin slice would be relatively simple, because you don't have atoms which are close to each other, so their interactions can be neglected. And why is this so? Because the atoms, they should be on some distance between one another. But if you have a thick sample, these atoms could be below one another, and then you have to process them. Processing simultaneously is a little bit harder. And that the multi-slice actually does that for you, because you cut the atoms and they don't interact anymore. Of course, they will interact when this slice is calculated, and then you go to the electron wave for the next slide, and that is already changed from the first atom and will go to the second. This is a derivation of the problem. Actually, this is considered as an operator equation. The important thing is this delta here, which is an operator. So that means you're considering this as an operator. And then you have that simply psi of z plus epsilon could be expressed through z, typical advancement in z. And then you have this operator, which is applied. If you apply that, here we have this v epsilon, which is just the thin slice, the VR in this thin slice. And then when considered, that is called the transmission function, which can be done so it is multiplied. And then practically, that is the Laplace operator is actually represented by this convolution of that. We're doing z-stepping, if you want to call it. And then we have that the next approximation on the z plus epsilon level can be calculated of the convolution of this kernel with the transmission function multiplied by the current value of the wave, and then seeing what is happening. So what is, as I said, the easy thing there is how we calculate this v epsilon that is simply considered the integral between z and z plus epsilon. And practically what usually is done is saying, okay, because z prime is somewhere in between, we consider epsilon is big enough so to capture the essential part of it. And very often people just consider the integral from negative infinity to infinity because actually the essential part of this v at that particular place is captured in the interval. That's again some approximation which pays off, and this is the kernel which is used in the convolution. We have propagation kernel and transmission function. We divide the specimen in several places. As I said, we calculate the particular v, and then this is what is happening. So that is this is one slice, this is another, this is a third one. So these are different slices, how there could be a lot of atoms in this. These are the heavier atoms, these are the not that heavy. This is also, if you can see, there are some different atoms, but you have different slices and we just progress through the slices. So
what is the intensity of the figure that you are using?
What?
How come some are more?
Because they're heavy atoms, they have much higher Z, and that means their potential is much bigger than the others. So that means if you have a gold atom and you have an oxygen, probably oxygen wouldn't matter, but that's what is happening. But sometimes if you have a lot of oxygen, of course, that will make some changes. So the multi-slice algorithm, we have to calculate this operator, and actually the thing is, instead of, so we're doing this step by step, we make the transmission step and propagation step, just calculating one after another, and as a result, we receive the wave in several different instances, and then we're interested in the last one, where this is the exit wave. So the propagation step is usually performed in Fourier space using fast Fourier transform. So this is very easy because this becomes multiplication here. The unfortunate thing is that usually the wave is very local. And because it's very local, you really don't need the whole space to do that. So if you have, if you calculate the electron wave, say in, say 100 million pixels, probably that's a little bit exaggeration, but if you want to calculate this precise, you might have only in a million pixels or even 100,000 pixels, which are important, which are where the electron wave is actually different from zero, essentially different from zero. And you want to calculate only this small part, and then calculating the Fourier transform for the entire sample, it's probably not very wise. Of course, we can eventually limit that application, but this should be taken special care of, and as you see, that sometimes it's problematic. We actually use a real space method when we calculate directly the convolution actually for the limited space, which actually pays up in some cases. So that is just to demonstrate what is happening. So that is the multi-slice algorithm. We start with, this is usually the initial wave. This is how the electron beam looks when there is nothing there. Then we go to the next. You might see there, probably if you're in the first row, that there are some distortions a little bit. These are some atoms which are passed through. Then we go, this is the next one. You can see already the distortions significantly, and then you see how the wave actually dissipates, and then after several, this is the last slide. So after several slices, you receive something like this, which is the exit wave. So, and then this is calculated, and we receive the results. Now, what is one thing which is actually very efficient in solving some other mathematical problems is the reduced basis method. The reduced basis method says the following. In general, I am considering it very general terms. You are solving some differential equation, but most of the solutions can be expressed as a linear combinations of a very small basis. usually in mathematics, this basis is not known. You have to consider the problem and try to see, which is usually a parametric problem with a lot of parameters, like here. Each atom is in the sample is a parameter for us. And we can consider what is happening with this parametric equation. Can we find some basis in which we have a smaller number of functions to calculate the solution for it, instead of calculating for 20 million different positions? If we have a reduced basis, we can calculate this reduced basis and then for each of these positions calculate everything there. So that is practically what is coming behind the prism. And that three key ingredients of that. First, we use that Schrodinger equation is actually linear with respect to the initial conditions. So if we have the sum of the solution, the psi, if we have a psi phi 1 plus b phi 1 instead of psi, then the solution would be the linear combination as well, which actually we use for the initial conditions. So we use the second thing is that the frequency, we have limit of the frequency of the initial wave. That means here we have this limitation that was the characteristic function of a small circle. And usually the number of frequencies which are considered here is much smaller than the number of probe positions. So for each probe position, we have to calculate what is happening, and then the number of frequencies is much smaller, and because of that, we can actually get away. And that is usually how the probe is using, that is in the real space, and that is in the Fourier space. You see how this is band limited, so everything is fine. So what is the idea? We solve the Schrodinger equation for, instead of solving it for all the probes, we are solving it for some delta function in the Fourier space, which are simply what are the elementary functions in this Fourier space. So how the Fourier transform is expressed. So we just choose these functions. We can solve for them and see what is happening. And then at the end, we know, okay, we know these linear combinations of all these functions. So in the example we had, this about 30,000. So these 30,000 functions, we can calculate what is happening to them, and then eventually calculate what is happening for this particular probe or any probe position everywhere else, because that would be still a linear combination of the same functions. So that is what we are doing, and then we have actually the set of the position and the set of these elementary functions. We have this inequality between their sizes, which is kind of essential. Here, this is the comparison between the initial waves and the classical multi-slice algorithm and the prism. The prism actually uses these elementary waves, and you could have different positions in different elementary waves. So you see these different examples. So what we're doing there, so we're solving the same equation as we solved before. However, the initial conditions are completely different. This is one of the elementary waves. Then it progressed through the atoms of the sample, and we receive something which is global, and have this exit wave. When this exit wave is calculated for all the elementary functions, we can make the linear combinations corresponding to our particular positions, and then can calculate what is going on. So the third thing which we're doing is that the proper wave functions is oversampled because of its rapid decay to zero. What that means? That means I said that we maybe have 30,000 elementary functions which describe that. However, if we reduce this number, so we don't use all these elementary functions, use a subset of them, eventually we can still have a very good approximation of all prop functions. Simply because it has a very fast decay, eventually not all the frequencies will play essential role, so we can do that. And this is actually, here is the original one when we have all the frequencies. And then we can say, okay, we subsample of the frequencies. We take every fourth frequencies. So we kind of sample twice this direction, twice that direction, and receive this function. It's not much different, actually, in the slide. You cannot see essential difference, but that's visual, of course, we have some. Here, maybe you can see this is a little bit of difference for f equals 4. That means 1/16, the number is reduced 16 times. Then you have 64 times reduction. You can see already that this is not a perfect function. So all experiments, Christian can confirm or decline that, but usually f equals 4 is kind of the optimal. F equals 8 is already a little bit too bad. And of course, if you go to 16, you see that this is not what you want to put as an input, so the error becomes too big. And the number of actually coefficients you use is very, very small. So you can use fast calculations for something which is not really important. So what is the summary? That we compute the solutions to the Schrodinger equation with some special initial conditions, which are for elementary functions, that is practically the elementary waves, then approximate the solution of the probe as we get this actually representation, which is pretty nice. So that means the coefficients, it turns out that they can easily be calculated with the Fourier transform of the initial wave. And then we have actually this one is the best approximation of what we of that function. And then, of course, when we have this for the initial wave, we make the same linear combination to approximate the exit wave.
Excuse me, Peter?
Yep.
So could you use principal component analysis to find like the optimal set of basis functions for these translated probes, or is it?
Yeah, okay. I'm diverting this question a little bit. I would say, okay, Christian will talk probably sometimes during the, because he's here at least until the end of the month, and maybe a little bit more, but I think that he will give a seminar about his results. I don't want to talk about these results. I'll mention a little bit about this. But yeah, you can use principal that's not that easy, because actually there are much more issues, and I'm exactly going to talk about these issues, which are way bigger than just choosing what is the basis. In fact, we tried to do that and found, and my recollection is that we were not much better than this choice. Actually, choosing different elementary functions instead of this, which are already chosen, is not giving a particular advantage in the calculations.
Yeah, so maybe the only thing I can add briefly now is that this Fourier space basis of these Dirac data that they use in the prism algorithm. This is actually, I mean, it's the best approximation of the Euclidean norm, and it actually is, I mean, if you use something like this, these sine functions to approximate, if you do this, if you use this to approximate the probes, then you're actually, if instead, so with the principal component analysis, I think what you get is like you get linear combinations of these sine waves, and then you want to form combinations of these linear combinations so that you can get less basis functions, so that you get better approximation. But this didn't really work very well. Yeah, so these Dirac data are actually a pretty good choice, but there are some other problems.
Yeah. Okay, so let's say what how we calculate the computational complexity. So we have usually n slices. That is kind of something we have it always. We have some propositions which depend on how your experiments you want to go. We have pixel discretization of the electron wave. Let me explain, because I didn't talk much about that, the pixel discretization, because usually when we think about the pixels, we're thinking about the proposition, because that's giving the image at the end what we observe. However, when we're solving the Schrodinger equation, we have to solve it in some mesh of points. And this mesh of points is this pixel discretization of the electron wave. So the electron wave, we want actually to receive it in a little bit better mesh, finer mesh than the mesh of the proposition. The proposition mesh is kind of the minimal one we could consider, but we want to consider it a little bit better, because that will give us the better approximation and eventually better results at the end. So we don't want to lose precision there. So we consider the pixel discretization, usually X is a pretty big number. And we have the interpolation factor. That means how much we subsample the elementary waves. And then we have subset of discrete probe frequencies. That means for this interpolation factor, we eventually have not the entire Q, all the elementary waves, we have some small portion of it. And then computing one-stem image will require, this is the number of the probe positions times the number of the slices times the, here we practically have plus x squared, a little bit more here with the log x, but that is what essentially is that. However, if we use prism algorithm, we have this QF, which is much smaller than P. We have N here, which is the number of slices, which is also that here. We have essentially this x squared again, and then we have an additional factor, which is P times QF times x squared over f squared. This number is essentially smaller than that one, because I said QF is essentially smaller, and then here the number of P positions is actually that factor. I think that if you apply prism for f equals 1, this is still an advantage because of the calculations. And here is the calculation. So at the end, when we get rid of this QF and we have the Q, and then, as I said, we have essentially better approximation when the number of the propositions is too high. And here is, in the prism algorithm, we see that in different factors. So that is what the probe looks like at the beginning. That is kind of the standard one. When you have the f equals 2, you practically we're introducing at the edges some additional probes. So we have 4 different probes, but because of the periodicity, we kind of match them. So the F equals 4, we have 16 more. Again, periodicity should be considered. And then we have more and more. And 32, we say. What, okay, I'll consider it here because what that means. That means that if these propositions, which are here, they interact with each other in the Fourier space, that is no longer a good approximation. If this is probably a little bit too much, this is okay, still okay, because we have that there is enough distance between them, so there is no essential values of the probes which are going there. And then, but here it's too much, and here it's simply impossible to get any good result. So this is kind of for different f, this is f equals 5. It is kind of on the limit of where it is used. And then in bright field, you see that the image is almost the same. The error is not that big. There are small differences here and there, but everything is fine. But when you consider the dark field, the things are dramatically worse than that. So you have the basic things again, but you see a lot of distortions, a lot of things which are not seen. So that for dark field is not a very good approximation. Okay, so what are the problems with practical problems? This is implicit propagation of the multi-probes may cause big errors, especially if f is essentially large. So the other thing is what I kind of neglected when I was presenting this, but the other thing is to say, okay, we calculate these thousands of different solutions and we have to store them somewhere. So typical example, keep in mind that x, this kind of moderate number, it's not a very big number for x, and q equals 1,000 means already, as I said, we usually had 30,000, q equals 30,000, that means it should be factor, should be made much smaller. That means if we have 30,000, that means practically about 5 point something, because it's a square root of the ratio. So that is already, this requires 32.5 gigabits of information. What we can do about it is is coming on the next slide. And then if we have the elementary waves, they're not localized. Because the elementary waves are not localized, that means we have to calculate everything for them. We have to calculate the full x square number of pixels which represent them. And that cannot be very good. So what we can do, first of all, we can explore further the idea of the reduced basis. So how we can explore further than that, we can actually consider the equation in a different way, how to define the reduced basis. For example, we can go there and say, okay, let's have the multi-slice method, but let's consider the solving the equation on a very specific subset of function, and solve it just through passing through one atom at a time. And then have this setup of solutions which are not very big, because they're, how many? I don't know whether you have 70, 80 atoms, you're different species you put into, can put into the sample. So that means you calculate very few solutions very well, but then you have a lot of combination times, because if you have 55,000 atoms in the probe, you have to apply this 55,000 times. The other way, which I think is the best, and Christian will talk about that, if we do, instead of elementary functions, we use the well-localized bases. So there are trigonometric bases which are well-localized, and if we apply for them, because the probes we are calculating are well-localized, and if we have well-localized bases to present them, this basis, we don't need the whole x square amount of pixels to know what is that. We can ignore significant part of them and then calculate only the small part of it. So it is, again, using the prism idea of the reduced basis, but now we have a good reduced basis which we don't need to know in too many, in a mesh which is that too big. So we can do that. We can use the propagation step, so that is the convolution. Also, because the convolution is also local operation, and if we have localized bases, we can also have this a little bit faster calculations than using Fourier transform. We can still use the Fourier transform, but in a smaller mesh and much more carefully, because keep in mind that the standard algorithm, when we consider Fourier transform, we initially usually have the periodic structure. We assume periodic structure of everything. Although that is not necessary, because if we have localization, we're perfectly fine. But if we don't have the localization, then this repeating structure is very good for the Fourier transform, because we don't have any errors in that. But when we have a very good localization, then it makes sense to apply the Fourier transform with a much smaller mesh, and because that will cost less computations. And then we have to find usually that all this, what I was talking about, is to make a good balance between the precision of the calculations and the amounts of computations. So that is something which we always have to keep in mind, that, and to be not too straightforward to go for the problem, but to think what is going here and there. And thank you very much.